Hey everyone, welcome back to Try Not to Sleep. I'm your host, Ethan Brooks, and as always, we're here with another calm, slightly boring story from history to help you unwind. Tonight, we will be talking about the question of whether humans might not be the first advanced civilization to develop on Earth. All right, get comfortable. And let's see how far you make it before you fall asleep. Earth formed about 4.5 billion years ago. The process began when dust and gas in the young solar system started to clump together. Gravity pulled these particles into larger and larger bodies. Collisions between these bodies created heat, and the growing planet melted and differentiated. Heavy elements like iron and nickel sank to the center, forming Earth's core. Lighter materials rose to the surface, creating the mantle and crust. The early Earth was extremely hot. Frequent impacts from asteroids and comets kept the surface molten. Volcanoes released gases, including water vapor, carbon dioxide, and nitrogen. These gases formed the first atmosphere. There was little or no free oxygen at this time. As Earth cooled, a solid crust began to form. Water vapor condensed and fell as rain, filling the low areas and forming the first ocean. This process likely took hundreds of millions of years. The oceans covered much of the planet's surface and helped regulate surface temperature. The moon formed soon after Earth, probably as a result of a giant impact. A Mars-sized body struck the young Earth. Debris from this collision coalesced in orbit and became the moon. The moon's gravitational pull stabilized Earth's tilt, affecting the development of the planet's climate and seasons. For hundreds of millions of years, Earth's surface remained hostile to life. Intense volcanic activity, frequent impacts, and a thin atmosphere made conditions difficult. But over time, the number of impacts decreased. The crust thickened and became more stable. Chemical reactions in the oceans and atmosphere began to create more complex molecules. These molecules set the stage for the earliest forms of life. By about 4 billion years ago, the first simple cells may have appeared in the ocean. Earth's long geological history had begun, shaped by constant change and powerful forces. For billions of years, life on Earth remained simple. Microbes dominated the oceans. These early organisms lived in environments such as hydrothermal vents and shallow coastal waters. They reproduced by dividing, and many used chemical energy from their surroundings. Around 2.4 billion years ago, some microbes developed photosynthesis. Cyanobacteria began releasing oxygen as a byproduct. Over millions of years, oxygen built up in the atmosphere. This event is called the Great Oxygenation Event. It changed the chemistry of the oceans and the air. Many early life forms could not tolerate oxygen and died out, but new forms adapted. By about 1.6 billion years ago, more complex cells appeared. These cells, called eukaryotes, contained internal structures such as nuclei and mitochondria. Eukaryotes could combine in new ways, forming colonies, and later multicellular organisms. For hundreds of millions of years, multicellular life remained small and simple. Most lived in the sea. Then, about 600 million years ago, the first large, soft-bodied organisms appeared. Fossils from this period, found in places like Australia and Newfoundland, show a variety of shapes and sizes. Around 541 million years ago, the Cambrian explosion began. In a short geological time, many new animal groups appeared. Hard shells and skeletons evolved, making fossilization more likely. Trilobites, early arthropods, and the ancestors of modern animals filled the oceans. Plants colonized land about 470 million years ago. About 470 million years ago. Fungi and simple animals follow. By 400 million years ago, the first forests covered parts of the continents. Insects and amphibians thrived in these new environments. Reptiles evolved next, adapting to drier conditions. By 250 million years ago, the continents formed the supercontinent Pangaea. Life diversified, but mass extinctions periodically reshaped the biosphere. Each extinction cleared the way for new groups to rise. Complex life continued to evolve, setting the stage for the age of dinosaurs. About 252 million years ago, the Permian-Triassic extinction event ended the reign of many earlier life forms. Over 80% of marine species and 70% of land species disappeared. After this event, new groups of reptiles began to diversify. Among them were the first dinosaurs, which appeared around 230 million years ago. During the Triassic period, early dinosaurs were generally small and bipedal. Over time, they evolved into a wide range of forms. Some became large predators, like Allosaurus and Tyrannosaurus. Others became massive herbivores, such as Diplodocus and Triceratops. Dinosaurs spread across all continents, including Antarctica, which was warmer than today. During the Jurassic period, about 201 to 145 million years ago, dinosaurs became the dominant land animals. Sauropods, the long-necked giants, roamed in herds. Stegosaurs and armored ankylosaurs grazed in forests. Predators like Ceratosaurus and Megalosaurus hunted in packs or alone. Birds evolved from small feathered dinosaurs during the Jurassic. Archaeopteryx, one of the earliest known birds, lived around 150 million years ago. This transition showed the close link between dinosaurs and modern birds. The Cretaceous period, from 145 to 66 million years ago, saw further dinosaur evolution. Flowering plants appeared and spread, changing ecosystem. New dinosaur species adapted to these changes. Ceratopsians, hadrosaurs, and raptors diversified. Some, like Spinosaurus, adapted to hunting in water. Dinosaurs were not the only dominant animal. Flying reptiles called pterosaurs filled the skies, and marine reptiles, such as plesiosaurs and mosasaurs, ruled the oceans. Mammals existed, but remained small and mostly nocturnal. For about 150 million years, dinosaurs were the largest and most successful animals on land. Their fossils are found on every continent. This era ended suddenly 66 million years ago, when a mass extinction event wiped out nearly all dinosaurs, except for the ancestors of modern birds. After the extinction of the non-avian dinosaurs, mammals diversified and spread into newly available ecological niches. Over millions of years, some mammals evolved larger brains, upright posture, and more complex social behaviors. The primate lineage appeared around 60 million years ago. By about 6 million years ago, the ancestors of modern humans diverged from other apes in Africa. Homo sapiens evolved roughly 300,000 years ago. Early humans used stone tools, controlled fire, and formed small hunter-gatherer groups. For most of human history, people lived by hunting, fishing, and gathering wild plants. They migrated out of Africa and colonized every continent except Antarctica. The development of agriculture began about 12,000 years ago in several regions, including the Fertile Crescent, China, and the Americas. People domesticated plants and animals, built permanent settlements, and formed larger communities. Cities emerged, and complex societies developed systems of writing, trade, and governance. Industrial activity began much more recently. In the late 18th century, the Industrial Revolution started in Britain. New inventions, such as the steam engine, spinning jenny, and power loom transformed manufacturing. Factories replaced handcraft production. Coal, and later oil, became the main sources of energy. Railways, steamships, and telegraphs connected cities and continents. Urban populations grew rapidly. Industrialization spread to Europe, North America, and eventually the rest of the world. Steel production, chemical industries, and electricity networks expanded. By the late 19th and early 20th centuries, automobiles, airplanes, and mass communication became common. Human industry began to alter the environment on a large scale. Deforestation, mining, and pollution increased. Fossil fuel use released large amounts of carbon dioxide into the atmosphere. The population grew from about 1 billion in 1800 to over 8 billion in the early 21st century. In just a few centuries, human industry transformed landscapes, climate, and the composition of the atmosphere. These changes left clear geological and chemical traces that future scientists can detect. In 2018, astrophysicist Adam Frank and climate scientist Gavin Schmidt published a scientific paper. They asked a specific question. Could Earth have hosted an industrial civilization long before human? They called this line of thinking the Silurian hypothesis, named after a fictional ancient civilization from a British television show. Frank and Schmidt examined the geological record for possible evidence of past industrial activity. They noted that human industry leaves certain signatures in sediments and rocks. These include rapid increases in atmospheric carbon dioxide, changes in carbon isotopy ratios, widespread plastics, synthetic chemicals, and radioactive fallout from nuclear testing. They pointed out that geological processes erase most physical evidence over millions of years. Fossilization is rare, and most artifacts decay or are destroyed by erosion, plate tectonics, and metamorphism. Even large cities could vanish without a trace after a few million years. Frank and Schmidt looked at specific events in Earth's history. One example is the Paleocene-Eocene thermal maximum, or PTM, which happened about 56 million years ago. During the PTM, a massive amount of carbon entered the atmosphere and oceans. Global temperatures rose, ocean chemistry changed, and many species went extinct. The causes of the PTM are not fully understood, but natural explanations, such as volcanic activity or methane release, are favored. The researchers asked whether the geological fingerprint of a past industrial civilization would be distinguishable from natural events like the PTM. They concluded that in many cases, the signatures could look similar. Fast carbon release, isotope shifts, and chemical anomalies might result from either industrial or natural processes. Frank and Schmidt did not claim that an ancient civilization existed. Their idea was a thought experiment. They aimed to test the limits of scientific methods for detecting civilization in the distant past. Their work showed that the absence of evidence is not always evidence of absence, especially when geological processes erase so much of Earth's history. Earth's surface is constantly changing. Plate tectonics move continents and recycle crust. Oceanic crust is especially young. None of it is older than about 200 million years. Continental crust lasts longer, but it is still subject to erosion, burial, and metamorphism. Over millions of years, mountains rise and wear down, and rivers carry sediment to the sea. Erosion is a powerful force. Wind, water, and ice break down rocks and transport material across the landscape. Even the largest structures, such as cities or monuments, would be reduced to rubble and dust over time. In some cases, entire regions are buried by new layers of sediment, which may later become rock. Subduction zones pull oceanic crust into the mantle. There, heat and pressure destroy any evidence of surface features. Volcanic eruptions can bury landscapes under lava and ash. Glaciers grind away soil and rock, scraping the land clean. Metamorphism alters the mineral structure of rocks. High temperatures and pressures deep underground change the original composition. Fossils and artifacts are often destroyed or transformed beyond recognition. Only the most durable materials can survive these processes. And even then, survival is rare. The fossil record itself is incomplete. Most organisms never fossilize. Soft tissues decay quickly, and only bones, shells, or teeth are likely to be preserved. Fossilization requires rapid burial in the right conditions, such as river deltas or lake beds. Artifacts made by intelligent beings would face the same obstacles. Stable environments, such as caves or deep-sea sediments, can sometimes protect remains for longer periods. However, these locations are rare. Over tens of millions of years, even these safe havens may be destroyed by geological activity. Because of these processes, most traces of past life and civilization vanish. Only a tiny fraction of Earth's history is preserved in rocks and fossils. This makes the search for ancient civilizations extremely difficult, even if they once existed. Fossilization requires a specific set of circumstances. Most living things decompose quickly after death. Scavengers, bacteria, and weather break down soft tissues. For fossilization to occur, rapid burial is usually necessary. Sediment from rivers, lakes, or volcanic ash can cover a body and protect it from decay. Hard parts, such as bones, teeth, and shells, have the best chance of becoming fossils. These materials resist decomposition longer than flesh or plant matter. Over time, minerals in groundwater may replace the original material, turning bone or wood into stone. This process, called permineralization, preserves the shape and structure of the original organism. Soft-bodied animals and delicate plants rarely fossilize. They leave little or no trace unless conditions are exceptional. Occasionally, fine-grained sediments or anoxic environments, such as deep ocean floors or peat bogs, can preserve impressions or even soft tissue. Amber, which is fossilized tree resin, sometimes traps insects and small organisms, preserving them in remarkable detail. Fossils are not evenly distributed across time or geography. Most are found in sedimentary rocks, which form in water-rich environments. Uplift and erosion can later expose these rocks at the surface, where paleontologists can discover fossils. However, vast regions of Earth contain few or no fossils because the right conditions never occurred. Artifacts made by intelligent beings face even greater challenges. Most human-made objects are perishable. Wood, textiles, and leather decay rapidly. Metals corrode and only stone tools. And ceramics have a reasonable chance of lasting for thousands or millions of years. Even these materials can be crushed, buried, or melted by geological forces. The result is a fossil record that preserves only a small, biased sample of past life and activity. Entire species, ecosystems, and possible civilizations could vanish without leaving clear evidence. This selectivity limits what scientists can learn from rocks and fossils, and it shapes our understanding of Earth's history. Scientists use chemical markers in rocks and sediments to learn about ancient environments. These markers include isotope ratios, trace elements, and unusual compounds. Stable isotopes of carbon, for example, can reveal changes in the global carbon cycle. When large amounts of carbon enter the atmosphere or oceans, the ratio of carbon-13 to carbon-12 shifts in a detectable way. This shift is preserved in sediment layers and fossil shells. Oxygen isotopes in marine sediments help reconstruct past temperatures. As the climate warms or cools, the ratio of oxygen-18 to oxygen-16 in ocean water changes. Marine organisms incorporate these isotopes into their shells. After they die, their remains settle on the seafloor and become part of the geological record. Other chemical clues include the presence of certain metals and synthetic compounds. Lead pollution from ancient mining or industrial activity can be detected in ice cores and lake sediments. Modern human activity has left a distinct layer of heavy metals, plastics, and artificial chemicals in recent sediments. These substances are called technofossils. Radioactive isotopes also provide information about past events. Natural nuclear reactors, such as those at Oklo in Gabon, created unique isotope patterns in rocks 2 billion years ago. In contrast, artificial radionuclides from nuclear testing since 1945 form a global marker in sediments and soil. During events like the Paleocene-Eocene thermal maximum, chemical signatures show a rapid injection of carbon into the atmosphere. Scientists debate the cause, with leading theories pointing to volcanic activity or methane release from ocean sediments. The resulting carbon isotope shift, warming, and ocean acidification are recorded in rocks worldwide. If an ancient industrial civilization had existed, it might have left behind unusual chemical markers. Synthetic organic compounds, plastics, or isotope anomalies could persist in certain environments. However, most chemical traces are diluted, altered, or destroyed by geological processes over millions of years. This makes detection difficult and uncertain. The Paleocene-Eocene thermal maximum, or PTM, occurred about 56 million years ago. During this event, a massive amount of carbon entered Earth's atmosphere and oceans over a few thousand years. Scientists estimate that between 3,000 and 10,000 billion tons of carbon were released. This carbon spike caused global temperatures to rise by 5 to 8 degrees Celsius. Evidence for the PTM comes from marine sediments and fossil soils found on every continent. These layers show a sharp shift in carbon isotope ratios, indicating a sudden influx of light carbon. The carbon likely came from volcanic eruptions, methane hydrates on the ocean floor, or the burning of organic-rich sediments. The exact source remains debated, but natural explanations are favored. The warming altered ocean chemistry. Acidification dissolved carbonate shells and disrupted marine ecosystems. Many deep-sea species went extinct. On land, forests and wetlands expanded toward the poles. Mammals and plants migrated to higher latitudes in response to the changing climate. The PTM lasted about 200,000 years. During this time, the carbon cycle gradually returned to its previous state. Sediments show a slow recovery of ocean chemistry and a return of carbonate deposit. Fossil evidence records the extinction and later recovery of many species. Scientists use the PTM as a reference point for understanding rapid climate change. The event's geological signatures include a global carbon isotope shift, temperature spike, ocean acidification, and mass extinction. These markers are similar to those produced by modern human activity, but the PTM's causes were natural. No evidence links the PTM to an ancient industrial civilization. The chemical and fossil records match patterns seen in other natural events. Researchers continue to study the PTM to learn how Earth systems respond to sudden carbon releases and to compare these ancient changes with current trends. Most scientists accept natural explanations for the PTM and similar events. Volcanic activity is a leading theory. Large igneous provinces, such as the North Atlantic Igneous Province, released huge amounts of carbon dioxide through eruptions and the heating of organic-rich sediments. This process injected greenhouse gases into the atmosphere over thousands of years. Another possibility is the destabilization of methane hydrates. Methane hydrates are ice-like compounds found in ocean sediments. When ocean temperatures rise or pressure changes, these hydrates can break down and release methane. Methane is a potent greenhouse gas that can quickly warm the planet. Evidence from PTM sediments suggests that both volcanic activity and methane release may have contributed to the carbon spike. Some researchers have studied the possibility of wildfires burning large peat deposits or organic-rich soils. These fires could have released additional carbon into the atmosphere. Charcoal layers in PTM sediments support the idea that wildfires played a role, but they were likely a secondary factor. Geological and chemical markers from the PTM are consistent with these natural processes. Carbon isotope shifts, temperature increases, and extinction patterns match what would be expected from rapid greenhouse gas release. No artificial compounds or manufactured materials have been found in PTM layers. The types of carbon and the distribution of chemical signatures also point to natural origins. Other mass extinction events, such as the Permian Triassic and Cretaceous Paleogene extinctions, show similar geological fingerprints. Volcanism, asteroid impacts, and climate shifts are well-documented causes. In each case, natural processes left clear evidence in rocks and fossils. Scientists continue to test new ideas, but the geological record overwhelmingly supports natural causes for ancient carbon spikes. The search for artificial signatures continues, but so far, no evidence suggests previous industrial civilizations affected Earth's climate in the distant past. Human industry leaves clear chemical and physical traces in the geological record. Since the Industrial Revolution began around 1750, humans have released about 550 billion tons of carbon into the atmosphere, mostly by burning fossil fuels. This rapid carbon injection has shifted the ratio of carbon isotopes in the air and ocean. Scientists detect this change in ice cores, lake sediments, and marine fossils. The resulting isotope signature closely resembles those produced by natural carbon release events, such as the PTM ion. Other markers of industrial activity include plastics, aluminum, concrete, and synthetic chemicals. Modern humans produce over 400 million tons of plastic each year. Plastics are durable and can survive in sediments for thousands or even millions of years. They form a new type of fossil, sometimes called technofossil. Aluminum production, which began on a large scale in the late 19th century, leaves unique mineral traces. Concrete, now the most widely used human-made material, alters soil and rock layers wherever it is used. Nuclear testing since 1945 has created a global layer of radioactive isotopes in sediments and soils. These artificial radionuclides, such as cesium-137 and plutonium-239, are distinct from those produced by natural processes or ancient natural reactors like Oklo. This radioactive signature is a clear marker of human activity and will persist for tens of thousands of years. Mass extinction is another industrial signature. Current extinction rates are 100 to 1,000 times higher than natural background rates. Many species have disappeared due to habitat loss, pollution, and climate change. This loss of biodiversity would be visible in the fossil record as a sharp decline in species diversity. Despite these distinctive markers, many industrial signatures resemble those caused by natural processes. Fast carbon release, isotope shifts, and chemical anomalies can result from both industrial and volcanic activity. This similarity makes it difficult to distinguish between natural and artificial causes in the distant geological past. Scientists have searched the geological record for signs of ancient industry. They examine sediment cores, rock layers, and fossil beds from many time periods. So far, no artificial artifacts or manufactured materials have been found in rocks older than the human era. There are no plastics, synthetic chemicals, or processed metals in ancient sediments. The only technofossils in the record date from the last few centuries. Researchers also study isotope ratios and chemical markers for unusual patterns. All known carbon isotope shifts and chemical anomalies in ancient rocks can be explained by natural processes. Volcanic eruptions, methane releases, and asteroid impacts are responsible for the major events observed. No evidence indicates the presence of large-scale combustion of fossil fuels or artificial compounds before humans. Fossil fuel deposits themselves provide another clue. Large reserves of coal, oil, and gas remain untouched in ancient strata. If a previous industrial civilization had existed and used fossil fuels, these resources would likely be depleted or altered. Instead, the distribution and composition of fossil fuels match what would be expected if they formed and remained undisturbed until recent human use. The fossil record also shows no sign of tool-using or technologically advanced species before humans. There are no fossil bones with artificial implants, no stone tools in pre-human layers, and no evidence of structured settlements or engineered landscapes from earlier eras. All known examples of complex construction or artifact production are linked to humans or their direct ancestor. On the Moon and Mars, where geological processes are slower, no artificial artifacts have been found. Lunar and Martian rocks preserve features for billions of years, but exploration has revealed only natural formations. If an ancient industry had left debris in the solar system, it has not been detected. All available evidence supports the conclusion that no industrial civilization existed on Earth before humans. The geological record contains only natural explanations for ancient anomalies. Scientists continue to investigate, but so far, the record is silent on ancient industry. Since the start of the Industrial Revolution around 1750, humans have burned large amounts of coal, oil, and natural gas. This activity has released hundreds of billions of tons of carbon dioxide into the atmosphere. The carbon in fossil fuels has a distinct isotopic signature. It contains less carbon-13 compared to carbon-12 because ancient plants preferentially absorbed carbon-12 during photosynthesis. As fossil fuel combustion increased, the ratio of carbon-13 to carbon-12 in the atmosphere began to decline. Scientists measure this ratio in tree rings, ice cores, and marine sediments. The decline is clear and rapid, starting in the late 18th century and accelerating through the 20th century. This shift is known as the Suez effect, named after the scientist Hans Suess, who first described it in the 1950s. Ice cores from Antarctica and Greenland preserve bubbles of ancient air. By analyzing these bubbles, researchers track changes in atmospheric carbon dioxide and isotope ratios over time. The data show a steady increase in carbon dioxide since 1750, with a corresponding drop in carbon-13. Marine sediments and coral skeletons record the same pattern, confirming that the change is global. The carbon isotope shift is one of the most distinctive chemical markers of human industrial activity. No natural process produces a similar pattern over such a short time scale. Volcanic eruptions and wildfires release carbon, but the isotopic signature and rate of change are different. Only the large-scale burning of fossil fuels matches the observed data. This isotopic fingerprint will persist in geological records for millions of years. Future geologists will be able to identify the onset of the industrial era by examining these shifts. The carbon isotope record provides clear evidence of human impact on Earth's atmosphere and climate, distinguishing the modern era from all previous periods in Earth's history. In the 20th century, humans began producing plastics on a massive scale. Plastics are synthetic polymers made from petrochemicals. They are lightweight, durable, and resistant to decay. By the 1950s, global plastic production reached 2 million tons per year. By the early 21st century, production exceeded 400 million tons annually. Plastics are used in packaging, construction, transportation, electronics, and countless other applications. After use, most plastic items are discarded. Many end up in landfills, rivers, and oceans. Some plastics fragment into microplastics, which are pieces less than 5 millimeters in size. Microplastics are now found in soils, sediments, and marine environments worldwide. Plastics do not biodegrade easily. Sunlight, heat, and mechanical forces break them down slowly. But the basic polymer structure can persist for centuries or longer. In the geological record, plastics can become buried by sediment. Over time, they may be preserved as technofossils, artificial materials that survive in rock layers. Other technofossils include concrete, aluminum, and synthetic chemicals. Concrete is the most widely used human-made material. It forms the foundations of buildings, roads, and bridges. When structures collapse or are demolished, concrete fragments enter the sedimentary record. Aluminum, once rare in nature, is now common due to industrial refining. It resists corrosion and can persist in sediments for thousands of years. Synthetic chemicals, such as polychlorinated biphenyls, PCBs, and pesticides, are also present in modern sediments. These compounds do not occur naturally and can be traced to specific industrial processes. Some are toxic and persist in the environment for decades. Together, plastics and other technofossils form a distinct layer in recent geological strata. This layer marks the presence of human industry and technology. Future geologists will identify these materials as evidence of an advanced civilization that altered the planet's surface and chemistry in the modern era. Aluminum is now a common element in the geological record, but it was once rare in nature. Before the late 19th century, aluminum existed only in compounds such as baurite ore. The development of the Hall-Héroult process in 1886 made large-scale aluminum production possible. This process uses electricity to extract pure aluminum from ore. As a result, the global output of aluminum increased rapidly in the 20th century. Aluminum is lightweight, strong, and corrosion-resistant. It is used in transportation, construction, packaging, and electronics. Discarded aluminum products accumulate in landfills and sediments. Unlike iron, aluminum does not rust easily, so it can persist in the environment for thousands of years. In many places, sediment layers contain aluminum fragments, shavings, and dust. These materials are unique to industrial activity and are not produced by natural processes. Concrete is another key marker of human industry. The modern form of concrete, known as Portland cement, was developed in the early 19th century. Concrete is made by mixing cement with sand, gravel, and water. When it hardens, it forms a durable material used for buildings, roads, bridges, and dams. Today, concrete is the most widely used human-made substance on Earth. Production exceeds 4 billion tons per year. When concrete structures are demolished or decay, fragments enter the soil and sediment. Concrete contains minerals and chemical additives that do not occur together in nature. These include calcium silicates, fly ash, and steel reinforcement bars. Over time, concrete pieces become buried and incorporated into geological layers. Both aluminum and concrete are resistant to weathering and chemical breakdown. They can survive in the geological record long after other materials decay. Future scientists studying rock layers from the industrial era will find these markers as clear evidence of widespread technological activity. These materials, along with plastics and synthetic chemicals, define the Anthropocene in Earth's stratigraphy. Nuclear weapons testing began in July 1945 with the detonation of the first atomic bomb in New Mexico, United States. Over the next several decades, countries including the United States, Soviet Union, United Kingdom, France, and China conducted hundreds of nuclear tests. Many of these explosions took place in the atmosphere, releasing radioactive particles into the air. These particles traveled around the globe, carried by wind and weather systems. Radioactive fallout settled onto land and water surface. Some particles entered the soil directly, while others washed into rivers and oceans. The fallout included isotopes such as cesium-137, strontium-90, plutonium-239, and iodine-131. These isotopes do not occur naturally in significant amounts and have specific half-lives. Cesium-137, for example, has a half-life of about 30 years, while plutonium-239 persists for over 24,000 years. Sediment cores from lakes, rivers, and ocean floors show a sharp increase in radioactive isotopes beginning in the mid-20th century. This layer is found worldwide, from remote polar regions to deep sea basins. Scientists use the presence of these isotopes to precisely date sediments from the nuclear era. The peak of radioactive fallout occurred in the early 1960s, before the Partial Test Ban Treaty of 1963 limited atmospheric testing. The nuclear fallout layer is distinct from natural radioactivity. Natural nuclear reactors, such as the Oklo reactors in Gabon, produced different isotope ratios and are more than 1 billion years old. In contrast, anthropogenic fallout contains artificial isotopes and matches the timeline of human nuclear activity. This global sediment layer is sometimes called the bomb spike. It serves as a clear, time-stamped marker in the geological record. Future geologists will recognize this layer as evidence of mid-20th century nuclear technology. The radioactive fallout, combined with plastics, metals, and concrete, marks a unique period in Earth's history that is unlikely to be confused with any natural event. Earth's surface is shaped by powerful geological forces. Erosion is a constant process. Rain, wind, rivers, and glaciers wear down rocks and soil over thousands or millions of years. Even the largest structures are broken apart and carried away. Human cities, monuments, and artifacts exposed to the elements eventually crumble. Their remains are scattered or buried under layers of sediment. Rivers transport eroded material to lakes and oceans. Sediments settle and form new rock layers. In some places, these layers preserve fossils or artifacts, but most material is lost or altered. Only a small fraction of what once existed survives long enough to enter the geological record. Plate tectonics also plays a major role in erasing evidence. Earth's outer shell is divided into moving plates. These plates collide, pull apart, and slide past each other. When oceanic plates meet continental plates, the oceanic crust is forced downward in a process called subduction. Subduction zones recycle the seafloor into the mantle. While any evidence on the ocean floor, including artifacts or technofossils, is destroyed by heat and pressure deep underground. No oceanic crust older than about 200 million years remains. Even continental crust, which can be billions of years old, is not immune. Mountain building, volcanic eruptions, and earthquakes can bury, deform, or melt rocks. Metamorphism changes the mineral structure of rocks, erasing original features and fossils. Large-scale events, such as landslides and floods, rapidly reshape landscapes. Glaciers grind down mountains and scrape away soil. Over time, coastlines shift and entire regions can be submerged or uplifted. Because of these processes, most traces of past life and civilization disappear. Only rare, stable environments, such as deep caves or rapidly buried sediments, preserve evidence for long periods. The dynamic nature of Earth's surface means that the geological record is incomplete. Most artifacts and structures are lost, making the search for ancient civilizations extremely difficult. Earth's crust is divided into two main types, oceanic and continental. Oceanic crust forms at mid-ocean ridges where magma rises from the mantle and solidifies. This process creates new seafloor, which slowly moves away from the ridge over time. As oceanic plates travel, they eventually reach subduction zones where they are forced beneath continental plates and recycled into the mantle. The entire cycle of oceanic crust formation and destruction takes less than 200 million years. As a result, no oceanic crust older than about 200 million years exists anywhere on Earth. All earlier ocean floors have been destroyed by subduction. This process erases any evidence that might have once existed on ancient seafloors, including fossils, sediments, or possible artifacts. Most of Earth's history, including the time of the dinosaurs and earlier eras, is missing from the oceanic crust. Only the youngest sediments and rocks remain, and even these are constantly being altered by chemical and biological processes. Hydrothermal vents, earthquakes, and volcanic eruptions further disturb and renew the seafloor. Deep-sea sediments accumulate slowly, often just a few millimeters per 1,000 years. These sediments can preserve microfossils and chemical signals from recent times, but older layers are lost as the crust is subducted. The oldest known oceanic crust, found in the western Pacific, is about 180 million years old. Beyond this age, all traces are gone. This continuous recycling means that any evidence of ancient civilizations or unusual events that might have occurred on previous ocean floors is permanently lost. Only continental crust, which can survive for billions of years, holds the potential for preserving the distant past. Even there, erosion and geological activity make preservation rare. The destruction of ancient oceanic crust is a major reason why the geological record is so incomplete, and why the search for deep-time civilizations faces such significant obstacles. Metamorphism is a geological process that changes rocks through heat, pressure, and chemical reactions. It occurs deep underground, where temperatures and pressures are much higher than at the surface. When rocks are buried by tectonic forces or covered by thick layers of sediment, they experience these intense conditions. Original features in rocks, such as fossils, sedimentary layers, or mineral grains, can be altered or destroyed by metamorphism. Bones, shells, and plant remains may be flattened, recrystallized, or dissolved. In some cases, the original material is replaced by new minerals, leaving only faint outlines, or no trace at all. Fossils that survive metamorphism are often distorted and difficult to identify. Metamorphic rocks form from pre-existing rocks, called protoliths. These can be sedimentary, igneous, or older metamorphic rocks. Common types of metamorphic rocks include schist, gneiss, and marble. The process changes the rock's texture, mineral composition, and structure. For example, limestone can become marble, and shale can become slate. Chemical reactions during metamorphism can concentrate valuable minerals such as gold, graphite, or gemstone. This process creates ore deposits that are often mined by humans. However, the same reactions can erase evidence of past environments or biological activity. Any artifacts or technofossils trapped in the rock may be destroyed or altered beyond recognition. Metamorphism is widespread in mountain belts, subduction zones, and the deep crust. It can affect large volumes of rock over millions of years. As tectonic plates move and collide, rocks are buried, heated, and later uplifted to the surface. When exposed, these rocks show little or no sign of their original features. The result is that much of Earth's history is obscured or lost in metamorphic rocks. This further limits the ability of scientists to find evidence of ancient life, environments, or possible civilizations in the geological record. Artifacts made by intelligent beings are fragile and easily destroyed. Most human-made objects are perishable. Wood, textiles, leather, and even metals decay quickly when exposed to weather, soil, and water. Only the most durable materials, such as stone, ceramics, or certain metals, have a chance of surviving for thousands of years. Even then, survival depends on the environment. Archaeologists find the best preserved artifacts in stable, protected settings. Dry caves, deep burial under sediment, and waterlogged environments can slow decay. For example, the Dead Sea Scrolls survived for 2,000 years in the dry caves near Qumran. In northern Europe, wooden tools and textiles have been recovered from peat bogs, where acidic, oxygen-poor conditions prevent decomposition. In Egypt, tombs sealed in dry desert sand have preserved papyrus, cloth, and even food for millennia. Deep ocean floors can also protect artifacts. Shipwrecks in cold, oxygen-poor water sometimes yield well-preserved wood, metal, and cargo. However, these environments are rare, and most artifacts that end up in the sea are quickly buried, corroded, or consumed by marine organisms. Burial under volcanic ash can preserve entire settlements. The Roman city of Pompeii, covered by the eruption of Mount Vesuvius in 79 CE, is a famous example. Ash-sealed buildings, objects, and even people, creating a detailed record of daily life. But such preservation is exceptional. Most artifacts never experience these ideal conditions. Erosion, scavengers, and chemical reactions destroy evidence before it can be buried or fossilized. Over thousands or millions of years, even the best protected sites can be disrupted by earthquakes, floods, or human activity. As a result, the archaeological record is incomplete and biased towards certain places and material. Only a tiny fraction of artifacts from past civilizations survive. This scarcity makes it difficult to reconstruct ancient cultures and almost impossible to detect civilizations from the distant geological past. Atlantis and Plato's story. The story of Atlantis comes from the writings of the Greek philosopher Plato. Around 360 BCE, Plato described Atlantis in two works, the Timaeus and the Critias. He claimed that Atlantis was a powerful and advanced civilization located beyond the Pillars of Hercules, which refers to the Strait of Gibraltar. According to Plato, Atlantis existed about 9,000 years before his own time. He wrote that the Atlanteans built great cities, developed sophisticated technology, and commanded a large navy. Plato said Atlantis attempted to conquer parts of Europe and Africa, but failed. Afterward, Atlantis supposedly sank into the sea in a single day and night of catastrophe. Plato presented the story as a moral lesson about the dangers of pride and the fall of great societies. He claimed to have heard the account from his ancestor Solon, who learned it from Egyptian priests. No ancient Greek or Egyptian records outside Plato's writings mention Atlantis. Later, Greek and Roman authors debated whether the story was true or fictional. Some tried to identify real locations as Atlantis, including islands in the Mediterranean, the coast of Spain, or even parts of North Africa. None of these theories match Plato's description in detail. Archaeologists and geologists have searched for evidence of a sunken continent or advanced civilization matching Atlantis. No such evidence has been found. The geology of the Atlantic Ocean shows no sign of a lost landmass of the size described by Plato. Underwater surveys and sediment studies reveal only natural features, such as mid-ocean ridges and seamounts. The story of Atlantis inspired many later myths and legends about lost civilizations. In the 19th and 20th centuries, writers and explorers proposed new locations, from the Caribbean to Antarctica. Modern science does not support these claims. Today, most historians and archaeologists agree that Atlantis was a fictional story created by Plato, not a real place or lost civilization. In the 19th century, scientists and writers proposed the idea of Lemuria, a lost continent in the Indian or Pacific Ocean. The name Lemuria came from the word lemur, because zoologists noticed similarities between lemurs found in Madagascar and India, but not in Africa or the Middle East. Some scientists suggested a sunken land bridge once connected these regions, allowing animals to migrate. Later geological discoveries, including the theory of plate tectonics, showed that continents move over time and that no such land bridge or lost continent existed. The idea of Lemuria was abandoned by mainstream science, but it persisted in occult and popular literature. Another lost continent, Mu, was described by Augustus Le Plongeon in the late 19th century. Le Plongeon claimed that ancient Maya texts referred to a sunken land called Mu in the Pacific Ocean. He linked Mu to the rise of ancient civilizations in Egypt and the Americas. However, scholars found no evidence for Mu in Maya texts or in geological surveys. The concept of Mu was promoted by later writers such as James Churchward, but it has no scientific basis. Flood myths are found in many cultures around the world. Stories of great floods appear in Mesopotamia, India, China, the Americas, and Australia. The best-known example in the West is the biblical story of Noah's Ark. In Mesopotamia, the Epic of Gilgamesh describes a catastrophic flood that destroyed most of humanity. Aboriginal Australians have oral traditions that recall the flooding of coastal lands thousands of years ago. Geological evidence supports the occurrence of large floods at the end of the last ice age. As glaciers melted, sea levels rose more than 100 meters, submerging coastal plains and river valleys. Some regions experienced rapid, catastrophic flooding, such as the Black Sea flood around 5600 BCE and the submergence of Doggerland between Britain and Europe. These real events likely inspired and shaped flood myths in many cultures. Oral traditions are stories, songs, and histories passed down through generations by word of mouth. Many cultures use oral traditions to explain natural events, remember ancestors, and describe changes in the landscape. In Australia, Aboriginal peoples have preserved stories about rising sea levels and the loss of coastal land. Some of these stories describe islands and landforms that were submerged over 7,000 years ago. Geological studies confirm that sea levels rose dramatically after the last ice age, flooding areas that were once inhabited. In northwest Europe, the submergence of Doggerland is well documented. Doggerland connected Britain to mainland Europe until about 8,000 years ago. As the climate warmed and glaciers melted, the North Sea expanded and covered this land bridge. Archaeologists have found stone tools, animal bones, and traces of ancient settlements on the seafloor. Local myths and legends from Britain and Scandinavia sometimes refer to lost lands beneath the sea. The Black Sea flood hypothesis is another example. Around 5600 BCE, rising Mediterranean waters breached a natural dam at the Bosporus. Salt water rushed into the Black Sea basin, raising water levels and flooding large areas. Sediment cores show a sudden change from freshwater to saltwater organisms, supporting the idea of a rapid flood. Some researchers suggest that this event influenced regional flood stories, including those in Mesopotamia. In North America, indigenous groups have stories about great floods and changing coastlines. These accounts often match geological evidence of glacial lake outbursts and rapid river changes during the end of the Ice Age. In Asia, Chinese legends describe floods that reshaped the Yellow River Valley, while Indian texts mention ancient deluges along the Ganges. Oral traditions preserve real memories of environmental change. Over time, Details can become mythologized, but the core events often reflect actual floods and landscape transformations. Archaeology and geology continue to uncover evidence that supports many of these ancient accounts. Doggerland was a vast landmass that once connected Britain to mainland Europe. It existed during the last ice age and for several thousand years afterward. The region stretched from what is now eastern England to the Netherlands, Denmark, and Germany. Rich in rivers, lakes, and marshes, Doggerland supported diverse animal populations and was home to Mesolithic hunter-gatherer communities. As the climate warmed around 12,000 years ago, glaciers melted and sea levels began to rise. Water from melting ice sheets flowed into the North Sea basin. Over the next several thousand years, the low-lying lands of Doggerland were gradually inundated. Archaeologists estimate that by around 8,000 years ago, most of Doggerland was underwater. Only higher areas, such as Dogger Bank, remained as islands for a time before being submerged as well. Evidence for Doggerland comes from several sources. Fishermen in the North Sea have dredged up bones of mammoths, reindeer, and other Ice Age animals, as well as stone tools and artifacts made by humans. Seismic surveys and underwater mapping have revealed ancient river channels, peat deposits, and remnants of forests buried beneath the seafloor. Similar stories of submerged worlds appear in other regions. The Sunda Shelf in Southeast Asia connected many islands during the Ice Age, forming a single landmass called Sundaland. Rising seas eventually separated Borneo, Sumatra, Java, and the Malay Peninsula. In the Americas, the Bering Land Bridge connected Siberia and Alaska, allowing people and animals to migrate between continents before it was flooded by the rising Bering Sea. These submerged landscapes shaped human migration and settlement patterns. Archaeologists continue to explore these underwater sites using sonar, submersibles, and core sampling. Each discovery adds to the understanding of how ancient peoples adapted to dramatic changes in their environment, and how much of human history now lies hidden beneath the sea. Göbekli Tepe is an archaeological site in southeastern Turkey. It was first identified in the 1960s, but its significance was not recognized until excavations began in the 1990s under Klaus Schmidt. The site is located on a hill near the city of Sanliurfa. Radiocarbon dating shows that Göbekli Tepe was constructed around 9,600 BCE, making it over 11,600 years old. The site consists of a series of circular and oval enclosures. Each enclosure contains massive stone pillars arranged in rings. Some pillars are over 5 meters tall and weigh up to 20 tons. The stones are decorated with carvings of animals such as foxes, snakes, boars, and birds. Other carvings show abstract symbols and human-like figures. The builders shaped the pillars from local limestone using stone tools. Göbekli Tepe was built by people who lived before the development of agriculture. At the time, humans in the region were still hunter-gatherers. No evidence of domestic crops or animals has been found at the site. Archaeologists have uncovered thousands of animal bones, mostly from wild gazelle, aurochs, and deer, suggesting that feasting took place during construction and use. The site was used for about 2,000 years. Over time, new enclosures were built on top of older ones. Around 8,000 BCE, the people who used Göbekli Tepe deliberately buried the entire complex under tons of earth and rubble. This act preserved the pillars and carvings in remarkable condition. No written records from the builders of Göbekli Tepe exist. The site predates the invention of writing by several thousand years. Nearby sites, such as Karahepe, Nalikore, and Kayonu, show similar stonework and may be part of a broader monument-building culture. Göbekli Tepe demonstrates that complex social organization and large-scale construction were possible before the rise of farming societies. Excavations are ongoing, and new discoveries continue to reshape the understanding of early human civilization. The people who built Göbekli Tepe left no written language or inscriptions. Archaeologists have not identified their names, their leaders, or the reasons for their construction efforts. The site itself covers about 22 acres, but only a small fraction has been fully excavated. Most of the enclosures and pillars remain buried beneath layers of soil and debris, protected from weather and erosion. Radiocarbon dating of organic material found in the fill and around the pillars confirms that the site was built and used between 9,600 and 1000 BCE. During this period, the surrounding region was home to small groups of hunter-gatherers. These groups likely moved seasonally, following herds of wild animals and harvesting wild plants. There is no evidence of permanent settlements, large villages, or organized agriculture at Göbekli Tepe. The construction of the stone enclosures required careful planning and coordination. Builders quarried limestone blocks from nearby outcrops using stone tools. Teams transported the massive pillars, some weighing over 10 tons, across short distances to the building site. The pillars were set upright in shallow sockets carved into the bedrock. Smaller stones filled the gaps between the large pillars, forming solid walls. Carvings on the pillars depict a wide range of animals, including snakes, scorpions, wild boars, and birds. Some images are naturalistic, while others are stylized or abstract. The significance of these carvings remains unknown, but they suggest a shared symbolic language or set of beliefs among the builders. Around 8000 BCE, the people of Göbekli Tepe deliberately buried the enclosures. They filled the spaces between pillars with rubble, soil, and broken stone tools. The reasons for this intentional burial are unclear. After the site was covered, later generations farmed and grazed animals on the hill, unaware of the ancient structures beneath their feet. The builders' identities and motivations faded from memory, leaving only the buried pillars as silent witnesses to their achievement. Göbekli Tepe is not the only ancient monumental site in southeastern Turkey. Archaeologists have identified similar sites nearby, indicating a broader tradition of large-scale construction during the early Neolithic period. One such site is Karahan Tepe, located about 50 kilometers southeast of Göbekli Tepe. Excavations at Karahan Tepe have revealed stone pillars, T-shaped monoliths, and carved animal figures. Some of these features are older, or at least contemporary with Göbekli Tepe. Other sites, including Nalikore and Kayonu, show evidence of communal buildings and decorated stone architecture. At Nalikore, discovered in the 1980s, archaeologists found rectangular buildings with stone walls, benches, and carved human figures. The site also yielded evidence of early farming, including domesticated wheat and barley. Kayonu, located in the foothills of the Taurus Mountains, contains stone-paved buildings and the remains of early animal domestication. Nahal Himar, in Israel, and sites in northern Syria, such as Tel Carmel, display similar architectural and symbolic traditions. Stone circles, communal enclosures, and decorated objects suggest that monument building was part of a wider cultural pattern across the Fertile Crescent. These sites date from about 11,000 to 9,000 years ago, a period of significant social and technological change. Archaeologists interpret these sites as centers for communal gatherings, rituals, or feasting. The construction of large stone monuments required cooperation among groups and may have reinforced social bonds. The presence of animal bones and food remains at these sites supports the idea of large communal events. The spread of monumental architecture in the region coincided with the gradual transition from hunting and gathering to farming and herding. As people began to settle and cultivate crops, new forms of social organization and religious expression appeared. The monuments and enclosures built during this time represent some of the earliest known examples of complex human society and shared symbolic activity. The builders of Göbekli Tepe and other early monumental sites left no written records. Writing systems did not exist during the time these structures were built, between 9,600 and 8,000 BCE. The earliest known writing, cuneiform in Mesopotamia and hieroglyphs in Egypt, appeared thousands of years later, around 3,200 BCE. Without writing, information about beliefs, rituals, leadership, and daily life was passed down orally. Archaeologists rely on physical evidence to reconstruct the activities and organization of these ancient communities. Stone tools, animal bones, and plant remains provide clues about diet and technology. The arrangement of pillars and carvings hints at shared beliefs or ceremonial practices. However, the meanings of the symbols and the reasons for the monument's construction remain uncertain. No names of individuals, tribes, or leaders are known from this period. There are no lists of offerings, prayers, or events. The absence of written records means that the motivations behind the deliberate burial of sites like Göbekli Tepe are unknown. Researchers can only infer possibilities based on patterns in the archaeological record. Oral traditions may have preserved some knowledge for generations, but spoken stories change over time. Without writing, details are lost or altered. Later farming and herding communities in the region seem to have been unaware of the buried monuments beneath their fields. The knowledge of the builders' achievements faded as new ways of life took hold. Other early Neolithic sites show a similar lack of written documentation. Carvings, figurines, and decorated objects are the main sources of information. These artifacts suggest complex social structures and shared religious practices, but do not provide direct explanations. The absence of writing limits what can be known about the people who built the first monumental sites. Their achievements are visible in stone, but their thoughts and stories remain out of reach. Archaeologists continue to study these sites, hoping to uncover new evidence that might clarify the lives and beliefs of these early builders. About 12,800 years ago, Earth's climate changed suddenly. This period is called the Younger Dryas. Before the event, the last ice age was ending. Temperatures were rising, and glaciers were retreating across North America, Europe, and Asia. Then, without warning, the warming trend reversed. Temperatures dropped sharply, especially in the northern hemisphere. The cold period lasted for about 1,200 years. Evidence for the Younger Dryas comes from ice cores, lake sediments, and pollen records. In Greenland, ice core samples show a rapid decline in temperature. Pollen studies in Europe and North America reveal a return of cold-adapted plants. Glaciers stopped retreating, and in some areas advanced again. The cooling affected rainfall patterns, causing drier conditions in some regions and increased flooding in others. Scientists have debated the cause of the Younger Dryas. The leading explanation involves changes in ocean circulation. Large amounts of meltwater from retreating glaciers entered the North Atlantic. This fresh water disrupted the Atlantic meridional overturning circulation, a major ocean current that moves warm water northward. With the current weakened or shut down, less heat reached northern latitudes, causing rapid cooling. Another hypothesis suggests that a cosmic impact triggered the event. Some researchers have found layers of microscopic spherules, melt glass, and high levels of platinum in sediments from the Younger Dryas boundary. These materials could result from a comet or asteroid impact. In 2024 and 2025, new studies of Baffin Bay sediments reported possible impact evidence. However, no large crater from this time period has been found. The debate continues, with many scientists favoring the meltwater hypothesis. The Younger Dryas ended as abruptly as it began. Around 11,600 years ago, temperatures rose quickly, and the modern warm period began. The end of the Younger Dryas coincides with the beginnings of agriculture and the construction of sites like Göbekli Tepe. The event remains one of the most significant climate shifts in recent Earth history. As the Younger Dryas ended, dramatic changes occurred in the animal populations of North America. Large mammals known as megafauna, including mammoths, mastodons, giant ground sloths, saber-toothed cats, and short-faced bears, disappeared from the continent. These extinctions happened rapidly, between about 13,000 and 11,000 years ago. The timing closely matches the end of the Younger Dryas and the beginning of the Holocene. The Clovis culture also vanished during this period. Clovis people are known for their distinctive stone spear points, called Clovis points, found across North America. Archaeologists date Clovis sites to between 13,200 and 12,800 years ago. Clovis people hunted large game, gathered wild plants, and lived in small, mobile bands. Their sites often contained the remains of mammoths and other megafauna, along with tools and butchered bone. After the Younger Dryas, Clovis points disappear from the archaeological record. Newer tool traditions, such as Folsom and Dalton, appear with different styles and smaller projectile points. These changes suggest shifts in hunting strategies and prey. The loss of large animals forced people to adapt to new environments and food sources. Scientists debate the causes of the megafaunal extinctions and the end of the Clovis culture. One leading theory is overhunting by humans. As people spread across the continent, they may have hunted large mammals faster than the animals could reproduce. Another theory points to rapid climate change at the end of the Younger Dryas. The warming climate altered habitats, reduced food sources, and stressed animal population. Some researchers propose a cosmic impact as a contributing factor. Evidence for this includes layers of microscopic spherules, melt glass, and high platinum concentrations in sediments from the period. However, no impact crater has been found, and the theory remains controversial. The disappearance of North America's megafauna and the Clovis culture marks a major turning point. Human societies adapted to new conditions, and the landscape changed permanently. The Holocene era began with smaller animals, new technologies, and the rise of farming in some regions. Scientists have studied the causes of the Younger Dryas and the rapid extinctions at the end of the Pleistocene for decades. One prominent hypothesis is the Younger Dryas impact hypothesis. It suggests that a comet or asteroid struck Earth around 12,800 years ago, triggering sudden climate change and widespread fire. Supporters of this idea point to layers of unusual materials found at many sites in North America and beyond. These layers contain high concentrations of platinum, microspherules, melt glass, and nanodiamonds. Such materials can form during high-energy impacts. In 2024 and 2025, researchers analyzed sediments from Baffin Bay in the Arctic. They reported evidence of impact-related materials, including spherules and shocked minerals. However, no large impact crater from this period has been found on land or under the ice. Some scientists propose that the impact could have occurred on the Laurentide ice sheet, leaving little or no crater in rock. Others argue that the evidence is better explained by natural processes, such as wildfires, volcanism, or even human activity. The impact hypothesis remains controversial. Many geologists and archaeologists support the meltwater pulse theory instead. This theory states that massive floods of glacial meltwater entered the North Atlantic, disrupting ocean currents and causing abrupt cooling. Ice core and sediment data show clear signs of large freshwater influxes during this time. The timing of these events matches the onset of the Younger Dryas. Debates also continue about the role of humans in megafaunal extinctions. Some researchers argue that overhunting by newly arrived human populations played the main role. Others believe that climate change and habitat loss were more important. There is no single cause that explains all regional patterns. Current research uses improved dating methods, sediment analysis, and genetic studies of ancient animals and plants. The debate over the Younger Dryas and its impacts continues, as new discoveries refine understanding of this pivotal period in Earth's history. Sudden catastrophes disrupt societies and destroy records. When disasters strike, people may abandon settlements, leaving behind tools, structures, and unfinished work. Floods, fires, earthquakes, and volcanic eruptions can bury or scatter physical evidence. Oral histories may be lost if survivors do not pass them on. In the absence of writing, knowledge is especially vulnerable to disappearance. Archaeological sites show clear examples of this process. The eruption of Mount Vesuvius in 79 CE buried Pompeii and Herculaneum under meters of ash. Buildings, artwork, and daily objects were preserved, but the lives and stories of most residents vanished. In the Bronze Age, the eruption of Thera destroyed the city of Akrotiri and disrupted societies across the Aegean. Written records from these events are rare or fragmentary. Floods have erased entire settlements. During the end of the last ice age, rising sea levels submerged coastal villages and hunting grounds. Doggerland, once home to Mesolithic communities, now lies beneath the North Sea. Artifacts and traces of habitation are preserved only where sediments covered them quickly. Most evidence was scattered or destroyed by waves and current. Earthquakes can collapse buildings and trigger landslides. In ancient Anatolia, the city of Troy experienced repeated destruction from both war and natural disaster. Each rebuilding phase covered older layers, making it difficult to reconstruct the full history. In Central America, volcanic eruptions repeatedly buried Maya cities, preserving some structures but erasing others. When societies collapse, written and oral traditions may not survive. The loss of scribes, libraries, and teachers can break the chain of knowledge. Over generations, memories fade and details become myth. Archaeologists rely on surviving artifacts, ruins, and environmental clues to piece together lost histories. Geological records confirm that most physical evidence vanishes after major catastrophe. Only rare conditions preserve detailed information. The result is that much of humanity's and nature's past remains unknown, shaped by the destructive power of sudden events. Fossil fuels formed over millions of years from the remains of ancient plants and animals. Layers of organic material were buried by sediments, compressed, and heated deep underground. This process created coal, oil, and natural gas. Major coal deposits date to the Carboniferous period, about 300 million years ago. Oil and gas formed in marine environments from the remains of plankton and algae. Humans are the only known species to exploit these resources on a large scale. Archaeological and geological evidence shows that ancient people used wood, charcoal, and animal fats for fuel. In some regions, such as China and the Middle East, small amounts of coal and oil were used for heating or as sealants thousands of years ago. However, systematic extraction and widespread use of fossil fuels began with the Industrial Revolution in the 18th century. Scientists have searched for signs of fossil fuel exploitation in older geological layers. They look for changes in sediment chemistry, evidence of mining, or residues from combustion. No such evidence has been found before the human era. Coal seams remain intact in rocks, dating back hundreds of millions of years. Oil and gas deposits show no signs of artificial disturbance or large-scale removal. If a previous industrial civilization had existed, it would likely have used easily accessible coal, oil, and gas. Large-scale extraction would have left physical traces, such as mine workings, tunnels, or altered rock layers. Chemical residues from burning fossil fuels would be present in sediments. None of these markers appear in the geological record before the last few centuries. The abundance of untouched fossil fuel reserves supports the conclusion that no earlier species exploited them on an industrial scale. The distribution and preservation of these resources match what is expected from natural geological processes. The absence of artificial disturbance in ancient coal, oil, and gas fields is one of the clearest indicators that humans are the first industrial civilization on Earth. Since the beginning of the space age in 1957, humans have sent spacecraft, landers, and rovers to the Moon and Mars. The Soviet Luna 2 became the first human-made object to reach the Moon in 1959. In 1969, Apollo 11 astronauts left equipment and footprints on the lunar surface. Since then, dozens of missions have explored the Moon's surface, including orbiters, landers, and robotic rovers from the United States, Soviet Union, China, India, and other countries. On Mars, spacecraft have been landing since 1971, when the Soviet Mars 3 made the first successful touchdown. NASA's Viking landers arrived in 1976, followed by a series of orbiters and rovers, including Pathfinder, Spirit, Opportunity, Curiosity, and Perseverance. These missions have examined Martian rocks, dust, and soil, searching for signs of water, life, and geological activity. Both the Moon and Mars preserve surface features for millions or even billions of years. The Moon has no atmosphere, wind, or liquid water, so objects left on its surface degrade very slowly. Mars has a thin atmosphere and occasional dust storms, but erosion is minimal compared to Earth. Impact craters, volcanic features, and ancient riverbeds remain clearly visible on both bodies. Exploration of the Moon and Mars has revealed no artificial artifacts predating human activity. All objects found on the lunar or Martian surface are natural rocks, meteorites, or features formed by volcanic or impact processes. No evidence of structures, tools, or manufactured materials from any non-human civilization has been detected. The only known artificial items are those left by recent space missions. Remote sensing, high-resolution imaging, and surface exploration continue to expand knowledge of both worlds. As of now, surveys and landings have covered only small portions of the Moon and Mars. But no unexplained artificial objects have been found. The absence of ancient artifacts supports the conclusion that humans are the first technological species to leave traces in the solar system. The fossil record documents the history of life on Earth for over 3.5 billion years. Paleontologists have collected and studied fossils from every continent. These fossils show the gradual evolution of bacteria, algae, plants, invertebrates, fish, amphibians, reptiles, birds, and mammals. Each group appears in the record at specific times, with clear transitions between major forms. No fossils of intelligent, tool-using species predating humans have been found. The oldest known fossils of the genus Homo date to about 2.8 million years ago in Africa. Earlier hominins, such as Australopithecus, show adaptations for upright walking but lack evidence of advanced tool use. Stone tools, made by early humans, first appear around 3.3 million years ago. These tools are simple and show gradual improvement over time. No evidence exists for non-human primates or other animals developing complex technology. Fossilized bones, teeth, and skulls of extinct species show no signs of artificial modification or implants. No fossil skeletons have been found with injuries or alterations caused by machines or advanced medical procedures. All known examples of worked bone, antler, or shell are linked to human or near human activity. Archaeological sites from the Paleolithic, Mesolithic, and Neolithic periods contain stone tools, hearths, and simple structures. These sites are always associated with anatomically modern humans, Neanderthals, or closely related species. There are no fossil sites with evidence of advanced metallurgy, synthetic materials, or engineered architecture before the rise of Homo sapiens. The fossil record is incomplete, and fossilization is rare. Most organisms leave no trace. However, the absence of fossils showing intelligent technological species before humans is consistent across all continents and time periods. The evidence supports the conclusion that Homo sapiens and their close relatives are the only species to develop advanced technology and leave a clear archaeological record. The geological and archaeological records show that Homo sapiens are unique in Earth's history. No other animal species has altered the environment on a global scale through technology. Human industry and agriculture have transformed landscapes, rivers, and coastlines. Deforestation, mining, and construction have reshaped ecosystems on every continent. Cities, roads, and dams are visible from space and leave lasting marks in the geological record. Humans have caused the extinction of many species through hunting, habitat destruction, and the introduction of invasive animals and plants. The current rate of extinction is 100 to 1,000 times higher than the natural background rate. This loss of biodiversity is recorded in sediments and will be visible to future geologists as a sharp decline in species diversity. Modern human activity produces materials never before seen in nature. Plastics, synthetic chemicals, and radioactive isotopes are now found in soils, rivers, and oceans worldwide. These substances form a new layer in sediments, sometimes called the technosphere. Plastics and aluminum fragments, concrete, and artificial compounds are preserved in recent geological strata. Radioactive fallout from nuclear testing since 1945 is a global marker that will persist for thousands of years. The use of fossil fuels has changed the composition of the atmosphere. Carbon dioxide levels have risen sharply since the Industrial Revolution. This increase is recorded in ice cores and marine sediments. The shift in carbon isotope ratios provides a clear chemical signature of human activity. No similar pattern is found in older layers, supporting the conclusion that industrial civilization is unique to humans. No evidence of advanced technology, synthetic materials, or large-scale environmental change appears in rocks older than a few thousand years. All known examples of complex tools, writing, and monumental architecture are linked to Homo sapiens or their close relatives. The available data indicate that humans are the first and only technological civilization to leave a clear global impact on Earth's geology. The current period is marked by a rapid loss of species. Scientists refer to this as the sixth mass extinction. Unlike previous mass extinctions caused by volcanic eruptions or asteroid impacts, the present event is driven primarily by human activities. Since the year 1500, at least 680 vertebrate species have gone extinct, according to the International Union for Conservation of Nature. Many more species are threatened or endangered. Extinction rates today are estimated to be 100 to 1,000 times higher than the natural background rate. The main causes are habitat destruction, pollution, overhunting, and the introduction of invasive species. Deforestation for agriculture and urban expansion removes forests and grasslands, reducing available habitats. Wetlands are drained for development, and rivers are dammed or diverted. These changes fragment ecosystems and isolate animal and plant population. Pollution from industry, agriculture, and households contaminates soil, water, and air. Pesticides, heavy metals, plastics, and other chemicals harm wildlife and disrupt food chains. Overfishing has depleted many fish populations in the world's oceans and lakes. Hunting and poaching have driven some mammals and birds to extinction. The spread of invasive species, such as rats, cats, and certain plants, has further reduced native biodiversity on islands and continents. Climate change, caused by greenhouse gas emissions, accelerates extinction by altering temperature and rainfall pattern. Coral reefs are dying due to ocean warming and acidification. Polar bears and other Arctic animals face shrinking habitats as sea ice melts. Many species cannot adapt quickly enough to survive these rapid changes. The fossil record will preserve evidence of this mass extinction. Sediment layers from the present era will show a sharp drop in species diversity and the sudden appearance of new materials like plastics and radioactive isotopes. Future geologists studying these layers will recognize the sixth mass extinction as a defining marker of human impact on Earth. The modern era leaves a distinct chemical signature in Earth's sediments and rocks. Since the mid-18th century, the burning of coal, oil, and natural gas has released vast amounts of carbon dioxide into the atmosphere. This change is recorded in the ratio of carbon isotopes, specifically a decline in carbon-13. relative to carbon-12. Scientists detect this shift in ice cores, tree rings, and ocean sediments. The isotope change marks the onset of the Industrial Revolution and is unique in the geological record. Other chemical markers include increased concentrations of nitrogen and phosphorus from fertilizers. These nutrients enter rivers and lakes, causing algal blooms and altering aquatic ecosystems. Sediment layers from the last century show spikes in these elements, reflecting the expansion of modern agriculture. Synthetic compounds also appear for the first time. Plastics, polychlorinated biphenyls, PCBs, pesticides, and pharmaceutical residues are now found in soils, riverbeds, and marine sediments worldwide. Many of these compounds persist for decades or centuries, resisting natural breakdown. They accumulate in food chains and can be detected in the tissues of animals from remote regions, including the Arctic and deep ocean trenches. Radioactive isotopes from nuclear testing and accidents form another clear marker. Isotopes such as cesium-137, strontium-90, and plutonium-239 are present in surface soils and sediments deposited after 1945. These isotopes do not occur naturally in significant amounts and are easy to identify in laboratory analysis. Their presence provides a precise timestamp for mid-20th century layers. Biological traces include sudden shifts in pollen and spores, reflecting changes in vegetation caused by land clearance and agriculture. Fossilized remains of domesticated animals, such as cattle, pigs, and chickens, become abundant in recent strata. The disappearance of certain wild species and the dominance of a few domesticated plants and animals are visible in both fossil and DNA records. Together, these chemical and biological traces create a unique stratigraphic layer. This layer will remain in Earth's geological record for millions of years, documenting the scale and speed of human impact on the planet. In the early 2000s, scientists began to discuss the idea of a new geological epoch called the Anthropocene. The term means age of humans. Paul Crutzen, a Dutch atmospheric chemist, and Eugene Stormer, a freshwater biologist, popularized the concept. They argued that human activities have changed Earth systems so much that the current epoch, the Holocene, no longer describes the present condition. The International Commission on Stratigraphy, which defines Earth's geological timescale, took up the question. In 2009, the Anthropocene Working Group was formed to study the evidence. The group examined rock layers, ice cores, and sediments for markers that could define the start of a new epoch. They looked for clear global signals that would be recognizable to future geologists. Several possible starting points were considered. Some scientists suggested the Industrial Revolution in the late 18th century, when fossil fuel use began to rise sharply. Others pointed to the mid-20th century, known as the Great Acceleration, when population, energy use, and pollution increased rapidly worldwide. The working group eventually focused on 1945 as the most precise boundary data. This year marks the first nuclear bomb tests, which left a global layer of radioactive isotopes in sediments and ice. The proposal for the Anthropocene is based on multiple lines of evidence. These include the presence of plastics, synthetic chemicals, aluminum, concrete, and technofossils in recent sediments. The carbon isotope shift from fossil fuel burning, the spread of domesticated species, and the decline in biodiversity are also key markers. These changes are global, rapid, and permanent on geological timescales. As of 2024, the Anthropocene has not been formally ratified as an official epoch. The debate continues among geologists, and stratigrapher. However, the evidence for a human-caused layer in Earth's geological record is clear and growing. The Anthropocene proposal reflects the profound and lasting impact of human activity on the planet's history. The geological record preserves the results of human activity, but it does not capture the details of culture, art, or knowledge. Layers of sediment and rock show the physical consequences of industry, agriculture, and urbanization. They contain evidence of deforestation, soil erosion, and the spread of invasive species. Pollen grains in lake sediments reveal the replacement of native forests by crops and pasture grasses. Charcoal layers mark the increase in wildfires, many started by human land clearing. Mining leaves scars on the landscape that are visible from the air and persist for centuries. Open pit mines, tailings piles, and abandoned quarries become part of the stratigraphy. Heavy metals from mining and industry accumulate in river and lake sediments. Lead, mercury, and arsenic concentrations rise sharply in layers deposited after the start of large-scale extraction and smelting. Urbanization produces concrete, asphalt, and brick fragments that are buried in floodplains, deltas, and coastal zones. These materials form artificial rock layers known as anthropogenic deposits. Landfills, filled with plastics, glass, and metal, create distinct strata that will remain long after organic materials have decayed. The construction of dams and reservoirs changes river sedimentation patterns, trapping silt upstream and reducing deposition downstream. The loss of biodiversity is recorded as a sudden drop in fossil remains of many species. Bones of extinct animals disappear from recent layers, replaced by the remains of domesticated species and a few adaptable wild animals. The extinction of plants and insects is visible in the pollen and spore record. The geological record does not preserve books, digital files, or works of art. Languages, scientific discoveries, and social structures vanish unless they are marked by durable objects or inscriptions. Over time, even the most advanced technologies break down and are lost to erosion, burial, or recycling by geological processes. What endures in the rocks is the evidence of environmental change and destruction, not the achievements of civilization. Scientific methods for detecting past civilizations rely on physical and chemical evidence. Researchers examine rock layers, sediments, fossils, and artifacts. They use radiometric dating, isotope analysis, and microscopy to identify changes in the environment and the presence of unusual material. These techniques are powerful, but they have clear limits. The fossil record is incomplete. Most living things never fossilize, and only a small fraction of past life is preserved in rocks. Artifacts and structures made by intelligent beings are even less likely to survive. While wood, textiles, and most metals decay quickly, only stone, ceramics, and some metals can endure for thousands or millions of years. And even these are often broken or altered by geological forces. Geological processes erase or obscure evidence over time. Erosion, burial, metamorphism, and plate tectonics destroy or transform rock layers. Subduction recycles oceanic crust into the mantle, eliminating any traces that once existed on the seafloor. Continental crust is older, but still subject to weathering, burial, and uplift. Most ancient surfaces are lost or deeply buried. Chemical markers, such as isotope shifts or synthetic compounds, can indicate unusual events. However, natural processes can produce similar signature. Volcanic eruptions, methane releases, and asteroid impacts all leave chemical traces that resemble those of industrial activity. Distinguishing between artificial and natural causes is difficult, especially when evidence is millions of years old. Synthetic materials and technofossils, like plastics and aluminum, are clear markers of recent human activity. But over geological timescales, these materials break down or are buried beyond reach. Only rare, stable environments preserve them for extended periods. Scientific archives may hold overlooked evidence, but most detection depends on what survives in accessible rock and sediment. The limits of preservation, detection, and interpretation mean that some past events or civilizations could remain undetected. The geological record is biased toward widespread, durable, and distinctive traces, and it is silent on most details of past life and culture. Natural events can erase or disguise the traces of civilizations. Volcanic eruptions cover landscapes with ash and lava, burying settlements and artifacts beneath thick layers of rock. Over time, these deposits harden and become part of the geological record, making it difficult to distinguish between natural and human-made features. Floods and tsunamis wash away buildings, roads, and tools, scattering debris over wide areas or depositing it in deep water where it may never be recovered. Earthquakes destroy structures and alter the course of rivers, submerging evidence beneath mud and silt. Landslides and avalanches can bury entire communities in moments. In some cases, rapid burial preserves objects for future discovery, but more often, it scatters or destroys fragile materials. Glaciers grind down everything in their path, crushing bones, artifacts, and even bedrock. When glaciers retreat, they leave behind a landscape stripped of earlier evidence. Meteorite impacts create craters and shock waves that vaporize or bury anything at the site. The force of an impact can melt rock, start fires, and trigger tsunamis. Any traces of life or civilization in the affected area are likely to be obliterated. Over millions of years, erosion and sedimentation further alter these sites, making original features hard to identify. Natural chemical processes also mask signs of civilization. Groundwater can dissolve metals and minerals, removing traces of construction or technology. Soil formation, plant growth, and animal activity mix and break down layers, blending artificial and natural materials. In some environments, acidic soils or water quickly destroy organic remains. Plate tectonics gradually moves, buries, and recycles the Earth's crust. Entire regions can be uplifted, folded, or subducted, erasing surface evidence. These processes work slowly, but are relentless over geological timescales. As a result, even large-scale civilizations could vanish without leaving clear or recognizable traces, their evidence hidden or altered by natural forces. Scientists recognize that the lack of evidence for ancient civilizations does not prove they never existed. The geological record is incomplete and selective. Fossilization is rare, and most artifacts decay or are destroyed before they can be preserved. Erosion, burial, and tectonic activity further reduce the chances that evidence will survive for millions of years. Even large cities, if left abandoned, would disappear quickly under natural conditions. Archaeologists and geologists rely on what is preserved and accessible. They search for artifacts, unusual chemical markers, and changes in sediment layers. So far, all known evidence points to natural causes for ancient anomalies, such as carbon spikes and mass extinction. No manufactured materials, synthetic chemicals, or engineered structures have been found in rocks older than the human era. The fossil record shows no sign of intelligent, tool-using species before human. However, scientists acknowledge the limitations of current methods. Most of Earth's surface has not been deeply explored. Many ancient layers are buried, eroded, or inaccessible. Deep ocean sediments, polar regions, and thick forests remain largely unexamined. Some markers of civilization, such as isotope shifts or rare compounds, could be overlooked or mistaken for natural processes. The Silurian hypothesis, proposed by Adam Frank and Gavin Schmidt, highlights these uncertainties. Their work suggests that even if an industrial civilization had existed millions of years ago, its traces could be erased or hidden by geological process. The absence of evidence is not the same as evidence of absence. Scientific conclusions are based on what can be observed, tested, and confirmed. Researchers continue to develop new techniques for detecting subtle signals in rocks and sediments. Advances in chemical analysis, imaging, and remote sensing may reveal new clues in the future. Until then, the search for ancient civilizations is limited by the nature of the geological record and the relentless forces that shape Earth's surface over time. The record of Earth's past is always fragmentary. Most organisms that lived on the planet left no trace. Only a small percentage of bones, shells, or plant material survived the processes of decay, burial, and fossilization. Archaeological sites are often discovered by chance, and many remain hidden beneath soil, water, or modern structures. Erosion, landslides, and construction can destroy sites before they are studied. Written records cover only the last few thousand years. Many ancient societies relied on oral traditions, which change or disappear over generations. Even when writing systems existed, documents could be lost in wars, fires, or natural disaster. Libraries, such as the one at Alexandria, were destroyed, erasing centuries of accumulated knowledge. Clay tablets, papyrus scrolls, and parchment manuscripts are vulnerable to moisture, insects, and time. Artifacts and monuments offer glimpses of past cultures, but interpretation is often uncertain. The purpose of structures like Stonehenge or the statues of Easter Island is still debated. Inscriptions may be missing, incomplete, or undeciphered, as with the Indus Valley script or the Rongorongo glyphs of Rapa Nui. Some archaeological finds, such as the Antikythera mechanism, reveal unexpected technological achievements, but their context remains unclear. Lost cities and civilizations are occasionally rediscovered. The ruins of Troy, Machu Picchu, and Angkor were unknown to the outside world for centuries. Underwater archaeology has revealed shipwrecks, harbors, and submerged settlements, but vast areas of the ocean floor have not been explored. In jungles and deserts, satellite imagery and LiDAR have identified hidden structures and ancient roads. Despite advances in technology, much of human and natural history will always be missing. The geological and archaeological records preserve only a fraction of what once existed. New discoveries continue to reshape understanding, but large gaps remain. The incomplete nature of the record is a persistent challenge for historians, archaeologists, and geologists. Since the late 18th century, human activity has altered the planet on a scale comparable to natural disaster. Industrialization began with the widespread use of coal and steam power. Factories, railways, and cities expanded rapidly. Deforestation cleared large areas of forest in Europe, North America, and Asia. Wetlands were drained, and rivers were dammed or diverted. These changes transformed landscapes and disrupted ecosystems. Mining operations removed mountains, excavated deep pits, and created vast waste piles. Open pit mines and quarries exposed rock layers that had been buried for millions of years. The extraction of metals, coal, oil, and gas released heavy metals and hydrocarbons into the air, water, and soil. Some mining regions, such as the Ruhr Valley and the Appalachian Mountains, became permanently altered. Agriculture intensified with the invention of new machinery and chemical fertilizers. Large fields replaced traditional patchwork farms. Monoculture crops became common, and natural vegetation declined. Irrigation projects changed the flow of rivers and lakes. The Aral Sea, once the fourth largest lake in the world, shrank dramatically due to water diversion for cotton farming. Urbanization covered land with concrete, asphalt, and buildings. Cities grew to house millions of people. Roads, airports, and industrial zones replaced natural habitats. Waste from cities and factories polluted rivers and coastal waters. Plastics, glass, and metal debris accumulated in landfills and oceans. Human activity increased the release of greenhouse gases, especially carbon dioxide and methane. These gases trap heat in the atmosphere, raising global temperatures. The result is rapid climate change, melting glaciers, rising sea levels, and more frequent extreme weather events. The scale and speed of these changes resemble those caused by volcanic eruptions, asteroid impacts, and other natural catastrophes. The geological record now contains clear evidence of human impact. Sediment layers show chemical pollution, radioactive isotopes, and technofossils. The marks left by human civilization are visible in rocks and soils around the world, recording a new and distinct chapter in Earth's history. Geological processes preserve certain markers of human activity for extremely long periods. Plastics, aluminum, and concrete are now widespread in soil and sediment layers. These materials are resistant to decay and can survive burial, compression, and chemical changes. Even as plastics break down into microplastics, their fragments remain stable and detectable in the geological record. Radioactive isotopes from nuclear testing since 1945 have spread globally. Cesium-137 and plutonium-239 are present in sediments, soils, and ice cores on every continent. Their half-lives mean these isotopes will persist for thousands to tens of thousands of years. The radioactive layer deposited in the mid-20th century will be a precise time marker for future geologists. Fossil fuel combustion has changed the composition of the atmosphere and ocean. The ratio of carbon-13 to carbon-12 in carbonate rocks, shells, and ice cores now carries the signature of industrial carbon release. This isotopic shift is unique to the last few centuries and is unlikely to be erased by natural processes in the near future. Elevated levels of nitrogen and phosphorus from fertilizers have also left chemical traces in lakes, rivers, and coastal sediment. Mass extinction is another marker that will endure. The sudden drop in biodiversity the disappearance of many large mammals, amphibians, and birds, and the dominance of domesticated species will be visible in fossil layers. Pollen and spore records will show the replacement of native forests with crops and pasture grasses. Urbanization has created thick layers of anthropogenic deposits. Landfills, construction debris, and artificial fill will become part of sedimentary rocks over time. These layers contain glass, metal, ceramics, and technofossil. Future geological processes will eventually bury, compress, and lithify these materials. Even as erosion and tectonics reshape the surface, the record of human civilization will persist deep underground. In millions of years, the distinct markers of our era will remain as evidence of a technological species that changed the planet. If intelligent life studies Earth in the distant future, they will find clear evidence of rapid change during the early 21st century. Drill cores from ancient lake beds, ocean floors, or buried floodplains will reveal the abrupt appearance of plastics, aluminum, and synthetic chemicals. Distinct layers of radioactive isotopes will mark the mid-20th century, corresponding to the era of nuclear testing. These markers will allow precise dating of sediments and rocks from this period. Chemical analysis will show a sharp shift in carbon isotope ratios, beginning in the late 1700s. Elevated levels of carbon dioxide and methane will be recorded in ice cores and fossil shells. Researchers will see a rapid increase in nitrogen and phosphorus from fertilizers, along with traces of pesticides and pharmaceuticals. The sudden appearance of these compounds will coincide with the decline of many wild species and the dominance of domesticated plants and animals. Fossil remains from this era will show a dramatic reduction in biodiversity. Many large mammals, amphibians, and birds will disappear abruptly from the record. In their place, the bones of cattle, pigs, chickens, and other domesticated species will become common. Pollen and spore records will document the replacement of native forests and grasslands by crops and pasture. Layers of concrete, glass, and metal will mark former urban areas. Landfills, construction debris, and technofossils will be preserved in sedimentary rocks. These deposits will be found on every continent and in many ocean basins. The distribution and composition of these materials will indicate widespread industrial activity. Future observers will recognize that these changes occurred over a short geological interval. They will be able to reconstruct the sequence of events that led to mass extinction, chemical pollution, and global environmental transformation. The evidence will show that a single species altered the planet's surface, atmosphere, and biosphere in ways unmatched by any previous event in Earth's history. The geological record of the human era will serve as a reference point for any future civilization that studies Earth. The markers left by industrial activity are global, durable, and distinct. Plastics, aluminum, and concrete will remain in sediments and rocks. Radioactive isotopes from mid-20th century nuclear testing will persist as a sharp, datable layer. The isotope shift from fossil fuel combustion will be visible in carbonate shells, ice cores, and sedimentary rocks. The mass extinction event caused by human activity will be clear in the fossil record. Many large mammals, amphibians, and birds will disappear in a short interval. Fossilized remains of domesticated animals and plants will dominate recent strata. Pollen and spore records will show the rapid replacement of native vegetation by agricultural crops and pasture grasses. These changes will be unlike any previous extinction event, both in speed and in the types of species affected. Chemical traces from fertilizers, Pesticides and industrial waste will be found in soils, lake beds, and river sediments. Microplastics and synthetic compounds will be present in marine and terrestrial deposits. These materials will distinguish the human era from earlier periods, even after millions of years of geological processes. Urban layers, landfills, and artificial fill will form new types of sedimentary rock. These anthropogenic deposits will contain glass, ceramics, metals, and technofossils, unique to the modern age. The construction and abandonment of cities, roads, and dams will leave patterns in the landscape that can be traced in future geological surveys. The record of the human era will show the consequences of rapid industrialization and global environmental change. It will provide data on the effects of carbon release, mass extinction, and the spread of synthetic material. Future civilizations, if they arise, will be able to study these markers and compare them to their own impact. The geological evidence left by humans will set a baseline for understanding the long-term effects of technological societies on a dynamic planet.